Hello, good day. Welcome back. Please join in to learn the embedded system on ARM Cortex M4 series. I'm sure you are revising the previous sessions and you're getting yourselves familiar about different registers and how the different bus works and what peripherals are connected, etc. So if not, please go back and revise and get yourself familiarized. So it will help you once you get moving with the next concepts. Today is day 16. We're going to learn about interrupt programming today. These are all the sections you will learn. First, you will learn what is an interrupt and how it is effective in the microcontroller, and the differences between the interrupt versus polling, and what is NVIC nested vector interrupt controller, what is external interrupt, what is a preemption, what is tail changing, and the example startup from scratch code using we're going to write two different interrupt codes, one for GPIO and the other for UART interrupt. So I'm sure at the end of this session you will be all more familiarized with how to use interrupt programming in your coding. Before jumping in, I would like to introduce to you a little bit about ourselves. I'm representing A2Digi. It's a startup by Anbukars brothers. My brother Alex and myself are all in 2023. Both of us gathered over 20 plus years industry experience, and we would really like to put it out there so to help you all out there so you can also build your newer version of yourself and becoming a better professional. Our mission is to convey our knowledge and our experience to at least about 100,000 future professionals through online courses. And the main advantage is you can study at your own pace wherever you are, so that is a really good advantage. A little bit about me. I am Arul Prakash Anbukarasu. You can call me as Arul or API, as persistent as I would like to be to share my experience and knowledge with you. I have 20 plus years of experience working in various industries in Australia, Singapore, Italy, and India in the renewable energy sector and solar and wind energy, power systems and lead acid batteries, network embedded systems on ATMs, TCRs, and POS, banking automation systems, smart parking operations, and my expertise lies on these three: embedded systems, VLSI, and project management. A small announcement to make. I categorized into two categories: the YouTube viewers and internship professionals. In order to get a free certificate, you have to at least watch 28 videos or attend 28 classes. At the end of every video session, there will be attendance link, so please fill that out and send it across to us, and that will count for your e-certificate attendance. Due to YouTube regulations, we can't keep all the videos out there all the time, so it has to be removed after 2 or 3 days. So in case if you missed a day and if you want to recap, unfortunately you'll miss out. So that's why I strongly recommend you and advise you to join one of our internship programs. And what will that acquire is to get you a internship certificate, and that's worth a lot. You will sit on top of everyone else in the interview queue, or also after landing into the first job you will be working with senior engineers. So these 30 days, it's very well worth spent in learning about a microcontroller. Not only that, you will have a separate login and you would be able to log into our learning management system portal, and you can go through every day session, and once you complete, click complete, and that will count for your attendance. On top of that, you will get unlimited access to all the course contents, to all the PDF materials, to the source codes, and all the other data manuals, reference manuals, etc. And also unlimited access to course videos. That means if you missed out on any session, you can always go back and watch it again and again. You can pause, you can come back and rewind. It's all yours to do it. So it's all yours to keep. And if you get stuck anywhere, please contact our backend support team, and they would be able to help you to make you move along in your learning curve. These are all the materials required. Still, if you haven't bought anything, please contact Pantech Solutions. They're a big manufacturing company. and they would be able to assist you to acquire all of this for you. The more you have hands-on on all project sessions, the more knowledge you uptake, and that helps you to come up with a lot of unique projects by yourself. So these materials doesn't stay only to this series. You can also use this, and you can create your own design, own project. So please invest on this, and it's money well worth spent, so you won't regret it. So shall we see what is interrupt is? Yeah, I'm sure you are keen, so let's get in and start to see what is this all about. Okay, interrupts. What is interrupts? As most of you would know by now, interrupts are a specific feature of microcontrollers that allows them to pause for few moments while in the frame of execution of the main program, and goes and executes a special routine called the interrupt service routine in response to a specific event. If something happened, then it stops the main program and goes to the ISR, and it executes that and then returns back to main program. Such as a button is pressed, for example, I connected the hardware, and so today one example is we're going to press this button, user button, and that will create an interrupt. So we're going to learn about how that is going to happen. So likewise, if there is a timer overflow or anything on the peripheral, then also you will get an interrupt. So these are all the three examples that you will learn about it today. You can configure any GPIO pin for interrupt. It doesn't have to be every pin is dedicated to that. No, you can configure any GPIO pin. And then you are transmit or receive, and then there is a timer overflow issues. If there is anything overflow, then you get the interrupts in that way as well. So this is in a nutshell. For example, if you're working on any emergency conditions, for example in a flood situation, or in a fire alarm, or in a flood situation, if your village or your town gets into floods, and the flood alarm will indicate to you there is something wrong. So at that time, the processor, for example, in that indicator will stop the main program and will throw alerts to all the outlets, letting people aware that there is a flood about to hit the village. So likewise also in the fire alarm system, and a fire breaks out in the building, then that causes an interrupt, and that will be alerted to the microcontroller. In other words, whenever an event occurs, the current program halts and gives attention to the ISR on the interrupt handler, and then it performs the interrupt handler and then comes back to main program. So that is an interrupt. Now we discuss about the interrupts versus polling. So there is two different techniques used in microcontrollers to handle external events. What are they? They are interrupts and polling. Interrupts are suitable for real-time analysis, whereas polling is non-real-time. It has to check every time. When we talk about polling, the microcontroller has to check every time whether any status of any external device or anything that happening. So it keeps checking on and on to check the status of the device, or if there's any change in the input or the output, then the microcontroller has to take appropriate action. So because of the constant check, it consumes a lot of processing power because it has to process all the time, whereas the interrupts are a mechanism that allows the microcontroller to temporarily halt the main program and goes into the ISR, the interrupt service routine, in response to a specific event. And then once it handles and finishes that interrupt event, it goes back to the main program and executes. So this is the main difference between interrupt versus polling. So interrupt is for real time, polling is for non-real time. interrupt, you can stop the program and you can go to the exception handler and you can finish that and then come back. Whereas in polling, it doesn't know what's happening, so the processor has to keep checking for the device updates to check for any changes, etc. So it consumes a lot of power, and also it's not for not real time. And all the interrupt service routines will be all listed in the startup code. So if you go in there and we learned about that previously in the sessions, how the vector table is placed and how the interrupts are placed in the table. So you have to follow that, and it stores on the starting point of the flash memory. If you remember, it will be on the starting point because it is in a full descending, as we know in this microcontroller, so it is on the starting point. As you all know that by now STM32F411 has 82 interrupts. Before going that, so this is just a structure of how the interrupt and the polling in the program works. So this is an interrupt. So in case of any event that happens while in the execution of the main program, it stops and then it switches to the interrupt service routine and it executes this data and then goes back. Whereas in polling, when it is in the main program, it keeps checking if the switch is on, if the input is coming through, etc. So therefore it doesn't fall into any more of the mode. So therefore it consumes a lot of processing power. So whenever it happens, then it may go to the ISR, but that's where the interrupt is really handy, so you can perform any event that occurs in the time of execution. So what is ISR? The function that gets executed when an interrupt occurs is called the interrupt service routine. Interrupt is nothing but it's also another function or the interrupt handler. So whenever an event occurs, then that goes into a special routine that's called the ISR, interrupt service routine. In ARM Cortex, there are 82 interrupts as you know, and 15 exceptions. In STM32F411, this particular one has got only 82 interrupts, but in general, ARM Cortex M4 can handle up to 240 interrupts. So the processor mode can change when exception occurs, and it can be in one of the following modes. It will be in the thread mode, that is a normal mode, and whenever an event occurs, it changes to the execute the handler, and therefore it will be in the handler mode. So these two are the whenever an exception happens, it moves to the handler mode. So thread mode is entered on reset, but the handler mode is entered on all other exceptions. So this is what the ARM processor is. So you can do by SVC handler, pend SCV, file system tick, and application code runs on the thread mode. Again, when it comes to the interrupt false, it executes by the order of the vector table that you already learned. And once it finishes the interrupt handler, then it moves back to the thread mode and it starts to execute the main program. In the exception behavior, this is how the exception behaves in the program. So first it's running the main program, and then there is an exception happens suddenly. So the main program will stop that, and then it will check what exceptions that is, and the exception according to its priority level, as you know, the lower the value is, higher the priority. So accordingly to that, the exception vector will move that to the exception handler, and the exception handler will start to execute. Once that finishes, the exception handler, then it puts back to the main program. So that's how the exception behavior works. So first main, and if any exception comes, then it checks for the priority according to the vector table, and then it goes to the exception handler routine, and once that finishes, and it goes back to the main. So that, and this is what explained in this few points. So what is NVIC? NVIC, as you know, it's a nested vector interrupt controller. It is a dedicated hardware that is present inside the core itself in the Cortex M microcontroller. It is mainly responsible for handling all the interruptions. So that's why it's there, and it directly communicates or connects to the interface with the microcontroller. And as you know, NVIC is one of the peripheral of the Cortex M process core. It is used to configure 240 interrupts, whereas in this case, we are learning STM32F411, which has got only 82 interrupts. So using these NVIC registers, you can either enable or disable or put into pending mode of the various interrupts that occurs, and read the status of every active and the pending interrupt. So it depends upon the registers what you are using. You can actually set into all of these different status of those interrupts. And again, you can configure the priority and priority grouping of various interrupts. It depends upon the vector table. You can see for yourself. The reset is the highest priority, so whenever if there is a reset, then that has to be on the top. Then the NMI non-maskable interrupt, then the others likewise. You can prioritize the various interrupts. It is called nested because it supports preempting. That means if a lower priority interrupt handler comes in and suppose the main program is executing and there is a lower priority that comes in, and the system stops, and then it handles that processor handles that lower priority, and then there is another higher priority interrupt arrives after a while. So what the processor will do at the time is it will preempt, meaning it will hold the lower priority interrupt for the moment, and then it will move to the higher priority, because being the higher priority it will accept that and it will execute that. So that process, it's called preempting, allowing something to happen from the current state to the new state. So that is what preempting is. So also that's what it's nested, because it can allow that interchangeability between the low priority to the higher priority. So that is, and if you check in the block diagram, it is this is the one illustrated in STM32. Components that are connected to NVIC include the I/O ports, and that has to be connected to the external interrupt controller, and the CSS, the clock security system interrupt, is connected to non-maskable interrupt lines. The peripherals, like the other peripherals, are connected directly to the IRQ lines, and the GPIOs are connected via the external event controller before connecting to the IRQ line. So this is how inside the NVIC the registers and different peripherals are connected, and the NVIC directly connected to the processor core via the system exceptions. The system ticker is connected directly to the IRQ. So these are all the steps that we learned already about how the exception and everything worked before, and this is the steps for user. When we talk about the NVIC, if you check on the reference manual, I'll go on the reference manual, just one sec. Reference manual, if you go okay, in the reference manual we need to go to NV control F, NVIC, NVIC. Always go to the contents, and you can go this way. Let's scroll down to go to, I want to show you page 198. So this is the nested vector interrupt. As you know, the priority -3 is reset, and then the NMI hard fault, etc. So the NVIC will have its register. So basically, it's a 32-bit register. It is an interrupt set enable register. If it is 1, then it will be set as the NVIC enable, and if it is 0, then that will be disabled. So there, for example, if there is 2 tasks happening at the same time, with the task A with the higher priority, then when task B comes through, then it means it could hold one of the value and then pushes the other value to do and make it work. So that's how the preemption works. So the preemption is, in other words, repeating again to say it gives way to the higher priority. When there is a lower priority, execution happens, and if something happens and the higher priority comes through, and it gives way to do that, it categorizes from IRQ1, IRQ2, IRQ3. So likewise it will go. So that's how it's done. That's the NVIC. These are the steps that you learned already to write a program, which you will see shortly. And these are all the NVIC registers. If you go to page 219, you need to have all these registers: the interrupt set enable register, the interrupt clear enable registers. There is the interrupt set pending registers, and there is the interrupt clear pending, interrupt active bit. So these are all the some of the registers that you will be using in the program. So NVIC registers, interrupt set enable register, you got to enable this. If it is 1, then the interrupt is enabled. If this bit is set as 0, then there is it means it will be disabled. In page 220, I guess. So I'll scroll down. Interrupt file. That's the register map. Here it is. That's data management, ISER. Interrupt set enable register, ISER. Let's go into the data sheet. I'm looking for the memory, no, not this one. System config AD CI2 CRTC. No. Maybe on this one, nuclear board. These are all the system control blocks. Cortex for fault handling, instruction set. If we go floating point, where are you hiding? NVIC, come out. Oh yeah, there it is, 4.2. So these are all the registers we just saw. Interrupt, nested vector interrupt controller, these registers. So if you come into the interrupt set enable register, so this bit has to be set as 1, means interrupt enable, 0 means it's disabled. So this is in the ARM Cortex M4 manual. So you need to go to page 219, 220, 221, and all these registers will be using it in the program. That's the interrupt set pending enable registers, ISPR. You will be using that too. And the next one is the interrupt clear pending enable registers, ICPR. The interrupt active bit registers, IABR. And these are all the external interrupts. The external interrupt can be fired either on these rising edge or falling edge, or on both. The we are going to use the push button. So as you know, the push button is connected to PC13. That's port C pin 13, and that's on 13th pin. So that is the exception external interrupt as 13. So if it is connected via anything by 0, that will be external 1 0. So likewise external 1, external 2, external 3, that's external 10. So we will be using external 13. So that's where the PC the push button is connected to. So that's what we'll learn by connecting your NVIC to 13, which is also an active low switch. So if you still go back to that manual, the PC 13 250 256 MP origin, it's a size. Okay, we'll learn about the program shortly, so I'll show you there. And you got to open the STM32Cube and I'll show you the rising edge and the falling edge, or it can be done on both. So whenever we push the button PC13, it should go to the interrupt service routine. So that's what you're going to learn from scratch. And the exception cycle. So this is how the real exception cycle work. Whenever an exception happen, it can either be a disabled by default behavior or enabled. Either be in pending state, that is a request is waiting to be served, or not pending state, or either be in an active being served currently, that it's holding on to the interrupt queue and it's doing it, or inactive state. So whenever an interrupt is fired, the interrupt will happen. The interrupt will execute that, and then suddenly if another interrupt arrives, so that current interrupt depends on the priority. If B is high priority, then the A will be set to pending state and then move to B. So accordingly, so you can also set by looking at the interrupt, you can set whether that's a must or must to do with priority values. So you can move that interrupt to pending or active or inactive state. So this is the exception life cycle. This is how it works. So continuing with exception exception life cycle, the lower priority ISR must wait in pending state until no higher priority, that is the no higher priority in processed. While it is been waiting, it can be put into either inactive state, that's the inactive state, or to the active state. The preemption happens when a task is abandoned. When a task, for example A, is abandoned or it gets interrupted, meaning in order to handle an exception, the currently running instruction stream is said to be preempted. So the currently running value will be stopped and it will allow or give way to the new priority execution. So when multiple exceptions with the same priority levels are pending, the one with the lowest exception number gets serviced first. So there are a few rules that you got to follow when the exception happens, and one of the rules is if they all have the same priority levels and they are pending, then accordingly the lowest exception number. So as you know, in the vector table there is exception numbers. So in that, if it is a -3, then that will do first. -2 is the lowest number, so that will execute first. And once an exception is active being serviced by the processor, the only with the exceptions with the higher priority can preempt it. So in other words, if you're working on, if the processor works on the low priority and if another low priority comes, then it won't preempt. It has to be a higher priority to preempt. So that's how the exception life cycle work. So this is the preemption. For example, there is 3 different tasks, the interrupt 1, interrupt 2 and interrupt 3. With time and priority we are talking about. So the main program will start to execute first, and then if there is a first interrupt happens, so the interrupt 1 will come and it will start to execute, but suddenly the interrupt 2 will occur, and the interrupt 2 will be a higher priority value. So that means the processor will stop this and it will do the interrupt to IR2 first, and then once it finishes, then it will move to the IR1, because interrupt 2 is the higher priority level. So this is the preemption. So it is working, and it's working on a low priority, and when suddenly interrupt to higher priority comes, and the main program stops it, and it goes to the interrupt 2 and it performs it. So likewise, once it finishes, then the second routine and the third routine happens, and once the third routine executes, then it goes back to the main program. So this is how the preemption works. The next important topic is tail chaining. This could be a very important topic, and sometimes you'll get an interview question related to tail chaining. Preemption and tail chaining, when you go for the fresher job, these two concepts are the must to know, and they will ask you in the interview. So what is tail chaining? When an interrupt occurs, the NVIC, the nested vector interrupt controller, branches to the corresponding interrupt service routine. So that happens on a normal execution. So normally after the ISR finishes, the NVIC return back to the main program. However, with the tail chaining, what will happen is the NVIC does not return to the main program after the first ISR, but instead immediately branches to the next higher priority pending request. So in other words, it will be extended. The interrupt request queue will be extended. In NVIC, the ISR will execute the interrupt and then puts back to the main program. But in tail chaining, it will check on the different level of interrupt requests further on. So if it finishes IRQ1, the interrupt 1, then it will go and work on the interrupt 2, and then it will move on, and once it all finishes, and as we learned already earlier, so once there is a request comes through, so that pushes to the stack. So pushing the data in is called stacking, and popping out of data is called pop out. It's called unstacking. So this is how the tail chaining happens. So first it finishes the first interrupt, and then it goes and finishes the second interrupt, and if there is another interrupt waiting there, then it will jump to interrupt 3. So it keeps extending. So that's what tail chaining is. With tail chaining, the NVIC does not return to the main program after the first ISR, but instead immediately puts to the next priority pending interrupt. This process continues until there are no more pending interrupts with a higher priority than the one that was just serviced. This will allow for efficient handling of multiple improved interrupts without the overhead of returning back to the main program each time. So it saves a lot of execution time, because every time you have to go back and come back, go back, come back. So it takes about another few more cycles to complete the chain. So that's what it explains here. The IR1 will IRQ1 will be performed in the ISR1 register. So likewise, tail chaining is extension. It won't go back to the main program. Okay, so now let's move on to learn about from scratch to create an interrupt, and we're going to use the GPIO and push button as your program. So whenever you push the button, it has to stop the main program and goes to that exception handler. It has to do that job, and once it finishes, it comes back to the main program. So that's how it will be. You will be learning about that today, and this is the block diagram to explain to you about the event controller. Whenever an event happens, how it works. So as you know, the peripheral bus is connected via the peripheral interface. Then it acts with all the pending request register. So once there is an interrupt comes through, it goes through the interrupt register and then the software interrupt. So likewise, it will switch from one register to the other register and calculates the value of the interrupts, and then come out as the input line. And these are all the interrupts that we learned already. So if it is external interrupt 0, then it has to be connected to the ext0. We are using ext13. The PC13 in the schematics is connected to PC13, so that's on the external 13 interrupt as a push button. So we need ext13 in the sysconfig. These are all sysconfig files. So how we going to deliver the interrupts to the processor? So every interrupt will be connected via the external interrupt, so via the GPIO pins, and the GPIO pin will be connected to the external pin accordingly to the 15 exception interrupts that has. So now we are using the exception 13, and that's from the peripheral side, so that will connect directly to the NVIC interrupt lines, and the NVIC will connect to the processor core, to the processor side. So you can enable or disable on the interrupt delivery to the processor. Likewise, you can also enable or disable the IRQ configured in the NVIC registers. So this is the example we're going to learn about how we're going to interface with the PC13, the push button 13, and for that you need to enable the external interrupt 13 bit sysconfig, and that's external 13 is connected to the exception handler from the microcontroller side to the processor core, and the NVIC is connected to the CPU, which CPU is nothing but the microcontroller. So this is how the enabling and pending of GPIO happens. And then these are all the steps you need to use to connect the button to create the interrupt. The button is connected to the GPIO C13 pin of the microcontroller, so the GPIO pin has to be configured to the input mode in mode register. Remember the register, the modes, the port mode can be done in 4 different modes: the input mode, output mode, alternate function mode, and analog mode. So in this case you're pushing as an input, as a push button, so it has to be configured to an input mode. Then there is a link between GPIO and the relevant XTI. That's the ext13 line must be established using the system config register, extic register. Then you have to trigger whether it happens on the falling edge or on the rising edge for relevant ext13, so you need to tell that, and then enable that external interrupt line in NVIC. Then implement the handler to service the interrupt. Then once it finishes, then clear the external interrupt pending register and goes back to the main program. And these are all the pointer variable declarations for system special function registers that you got to use. So you will be learning shortly about how you're going to program everything from line 1. You're going to learn and you're going to program. So this is the program to illustrate, which I will show you shortly. And also the next one you're going to the first exercise is to push the button and create the interrupt, and the second exercise will be using the USART2. So the USART2 IRQ number is 38. By the external peripheral you're going to create that interrupt and then connect to the NVIC, and how that interrupt happens. So these two will be the learning today. So I think we are going a little bit longer, so I'll give you that deserved break. So go and enjoy that break. When you come back, I'll show you line by line execution of the interrupt creation, and you will see that in the IDE. So I'll catch you shortly in about a couple of minutes. Until then, take care. I'll catch you shortly. So go and enjoy that break. I'll catch you soon.